we start multivariable calculus. That is calculus in higher dimensions. For our purposes, we will look at 3 dimensions, and sometimes we will look at higher dimensions. But what is the 3-dimension coordinate system? So far, you are accustomed to the 2-dimensional coordinate system, consisting of points in the plane represented by an ordered pair, AB. So you have 2 axes, X and Y. And any graph here is called a curve in R2. So what about the 3-dimensional coordinate system? Here we look at points in a plane, or points in space, represented by an ordered triple A, B, and C. And this system is called a 3-dimensional coordinate system. The graph is a surface in R3. So the vertical axis is the Z-axis, this one is the Y, this one is the X. Sometimes the X and Y are interchanged. These only represent the positive axes. I did not extend it to represent to show the negative axes. Now, if you look at these axes here, those 3 axes form the coordinate planes. So for example, that X and Z axis, this plane on this side is called the XZ plane here. And sometimes the XZ plane is defined as Y equals 0, the plane Y equals 0. The plane comprising of the Z and Y axis is called the YZ plane, or the plane X equals 0. And the plane comprising of the X and Y axes is called the XY plane, or the plane Z equals 0. Any questions so far? Okay, so let's plot points. We all know how to plot points in the 2-dimensional coordinate system. What about the 3-dimensional coordinate system? Yes. Okay. So let's plot the points P equals 1, 2, 3. So draw your axes. So this is the Z, this is the Y, this is the X, and of course this is the origin, okay? So the point 1, 2, and 3 means it's 1 on the X-axis, so let me just find 1. 2 on the Y-axis, so put in your 2. And you want 3 on the Z-axis. Okay, so let's see how we're going to go. So you need to draw, you're going to get the hang of that very easily. I'm sure some of you can see where the point is, but it's like you need to draw a cuboid. Let me use a different color to draw the cuboid, and then we'll plot the point in a little bit. Okay, I'll use this color. Okay, so we have 1 and 2, so draw a little parallelogram for 1 and 2 here. Okay. And then extend it up there by the 3 here. Here. And then do the same thing here. Like that. And then this point here is your point P. 1, 2, 3. Okay. Now let me speak about other points that you may see. Since I have that cuboid here, let me look at other points here. This point here is the projection of P onto the XY plane. Here. Projection of P onto the XY plane. This point here is a projection of P onto the XZ plane. And finally, this point here is a projection of P onto the YZ plane. Okay. So that's how we plot points. Do you have any questions here? Because you want to go 1, 2, and up 3. You see, 1, this is the point P because it's 1. You go 1 here, go across 2, and go up 3. Got it? Okay, let's move on. What do surfaces in R3 look like? There are some really intricate surfaces, but let's really start with the basic surfaces. The more difficult ones, we will draw them on the calculator. All right, but there are some that we can draw by hand. Okay, let's change the color back. Let's start sketching some planes. We want to sketch the plane z equals 2. So let's draw the axes. Z, Y, X, sorry, this is X. And this is 0. So z equals 2, we're really looking at the set of all points x, y, z, where z is 2. Right? So z is the only coordinate that is fixed. X and y could be anything. So therefore, you look at 2 here on the z-axis, and all you're going to do is to draw a horizontal plane through 2. So let me draw it in blue. So maybe something like that. More or less. And so we can describe it as a horizontal plane parallel to the XY plane and 2 units above it. So that's the plane z equals 2. Let's draw the plane y equals 3. Any questions on that first plane? Okay, y equals 3. Let's draw your axes again. Z, X, Y, 0. And so what are you going to draw? The only fixed coordinate is 3. So you look for 3 on the y-axis. and draw a plane through 3. So maybe something like this. So let's describe that plane in words. Can somebody describe it for me, like I did in the first case? Vertical plane, parallel to XZ plane, 3 units where? To the right of it. Okay. Now let's describe that plane, or it's the surface actually. The surface is Z greater than or equal to 0, less than or equal to 6. So this is basically a region between 2 planes. All right, so we just say the surface is a region which lies between 2 planes, Z equals 0 and Z equals 6. Between and including, correct, because there's an equal sign here. Let me just put an including. An inclusive of. Good. Good observation. Questions? Okay, let's move on. Let's look at some common surfaces that you need to recognize. You know, like in the two-dimensional coordinate system, you need to know the equation of a circle with center 0, 0. You need to know these things for the three-dimensional coordinate system. All right, so the 2 most popular ones are spheres and cylinders. So a sphere is like a circle in 3D. All right, so let's look at this. An equation of a sphere in R3 with radius r centered at ABC is x minus a squared plus y minus b squared plus z minus c squared equals r squared. You have seen something like this before in R2. An equation of a cylinder in R3 with radius r and central axis, the z-axis, is x minus a squared plus y minus b all squared is r squared. Notice that z is missing. And we're going to draw these type of cylinders so you'll understand what I mean when I say the central axis is the z-axis. Let's look at some examples. Some of them we'll draw, some we won't draw. Number 1, we will not draw. We will just explain. What region is represented by x squared plus y squared plus z squared equals 4 and y greater than 0? So let's look at the first function here. X squared plus y squared plus z squared equals 4. What is that? Sphere, radius 2. Very good. Centered at the origin, right? But what is this y greater than or equal to 0? What is that saying? So look at, let me just draw the axes. This is y, x, z. Y greater than or equal to 0.
Otherwise it just be a circle.
Yes, but you kind of say otherwise it will be as, how would you describe it? What does the y greater than or equal to 0 tell you about the sphere? Where does it lie? It lies half, we don't say circle in 3D. Our sphere is lying to the right of the XZ plane. Right? So let's write that. So sphere of radius 2 centered at the origin, lying, I would say, on the positive side of the XZ plane. Let's look at number 2. X squared plus y squared equals 4. This is a cylinder. But let's see why. There's no restriction on the z, right? If there's no z there, that means there's no restriction on the z. Now, if this was not in 3D, how would you describe that function? Anybody? It's a circle. Continue. Center the origin, radius 2. Okay? So since there's no restrictions on the z, what we are looking at is that type of circle in any horizontal plane, z equals, say, any constant. So you have circles of that nature moving throughout the z-axis. So you're going to have something like this. Let's draw our z, y, x. I'm going to extend the z down that way. Okay? So let me use this here, different color. So you'll have a circle. Let's start here. Center the origin with radius 2, and you move it vertically. Okay, and then you will form a cylinder. So that is why we say it is a cylinder whose axis is the z-axis. Central axis, z-axis. So cylinder whose central axis is the z-axis. Actually, the mathematical term for this, we call it a right circular cylinder. Right circular cylinder. And I will say, let me just be more specific. We didn't speak about the radius, so let me just say right circular cylinder of radius 2 with central axis the z-axis. Okay. Okay. Any questions? Let's do some more. Y squared plus z squared equals 1. What do we have here? Another cylinder. What's the central axis here? X-axis. Okay. So what do we have here? Let me just put this. We have circles, radius 1. Of course, center the origin, going along the x-axis because there's no restriction on the x-axis. So you can draw it. Just let me extend the x-axis backwards. Okay. Just let me do this for all of the axes, okay? Okay, so we have, let me use another color. So we have a circle, radius 1, center the origin, and just move it along, right? And so on. And you just draw it. Okay, so describe it. Right circular cylinder of radius 1 with central axis the x-axis. Okay, and let's look at number 4. X squared plus y squared equals z. Now, what does that look like? Okay, let us draw our axes first of all. All right, so we have x squared plus y squared. That looks good, but there's the z on the right. If we had x squared plus y squared equals some constant, that would not be a problem, right? But there's a z. So how do you handle the z on the right? Give that z certain values and draw the corresponding shape for these values. So for example, when z is 0, what do you have? X squared plus y squared equals 0. Which means what are the values of x and y? 0. So therefore, when z is 0, you have a point at the origin. Go on. When z is 1, what do you have? Circle center the origin, radius 1. So at 1, you draw a circle, center the origin, radius 1. Let me use a different color here. And continue. When z is 2, for example, or even 4, let's do 4. What do you have? Circle radius 2. And it continues. And I'm hoping you are seeing what's going to happen. Right? You will have a shape looking something like a bowl. But we do not call it a bowl. The mathematical name is a paraboloid. A paraboloid. Paraboloid. Opening upward. Okay. There are some basic concepts that I will just look at briefly. The distance formula, you can find the distance between 2 points the same way you did it in 2 dimensions. So this is the formula. So between P and Q is the square root of the sum of the difference of the squares. Okay? So if I have to find the distance between the point P145 and Q365, what do we have? The square root of 1 minus 3 squared plus 4 minus 6 squared, plus 5 minus 7 squared. That is equal to the square root of 4 plus 4 plus 4, which is square root 12. Okay. Any questions here? Okay. Let's start by looking at vectors, or let's continue by looking at vectors. Vectors form an integral part of this course. So you need to know what a vector is. You need to know the operations on vectors. What is a vector? It's a quantity that has both magnitude and direction. So let's just draw a line from A to B. And it has direction, so let's put an arrow going like that. This is called the vector AB. Like that. Put an arrow on top of it. And this is equal to, let's call this vector A, little a. Now usually in your textbooks, the normal notation for vectors is something in bold. But because I can't do anything in bold, you can either put a line underneath it, or you can put an arrow on top. It does not matter which one. Okay, something like that. By the way, if I had to, the vector BA, if I had to reverse the direction, BA is negative A. Okay? Let's add vectors and subtract vectors. We do both of these by using either the triangle law or the parallelogram law. That is, and it's explicit. The triangle law, you form a triangle. The parallelogram, you form a parallelogram. So let us look at the triangle law first. Okay? Let's draw. This is A, B, C. Let's draw that triangle. So let's put an arrow from A to B and an arrow from B to C. And then let's call AB vector little a and BC vector little b. The triangle law says that AB plus BC is equal to the vector AC. That's the triangle law. How do I know that? For you to use the triangle law, these two letters must be the same, right? And the resultant vector would be the letters on the outer edges. Good? And so AC is the vector here. Now note this also. For you to use the triangle law, the two vectors that you are adding, the arrows must follow. Okay? As you can see, they follow. And then the resultant vector, the arrows in the other direction. It does not follow. That's the only way you can use the triangle law. Alright? The parallelogram law, on the other hand, the arrows should not follow. They should diverge from a point. So for example, let's call this AB again. Let's call this A. And then let's call this AC. B. Notice the arrows for AB and AC are diverging, right? You can add AB and AC in this case by forming a parallelogram. Okay, so you be careful. You can't use the triangle law there as such. It's better to use a parallelogram. So what you do, you draw, you complete a parallelogram like that. And then this, oh, what happened here? This is red. This line here, this vector is A plus B. That is a parallelogram law. Okay, let's subtract vectors now. Again, I will illustrate the subtraction of vectors using both the triangle and the parallelogram law. Okay, so what if I gave you, so let me just say I want to illustrate A minus B. Okay, that's what I want to show. And then I'm going to give you the vectors like this. This vector is A, and this vector is B. Okay. If I complete the parallelogram as is, I'm going to get A plus B. That's not what I want. I want A minus B, right? So remember what minus B is? Same length, but in an opposite direction, right? So form a minus B like that. Go like that. So this is your minus B. Now complete the parallelogram. With a straight line as best as you can, not like mine. And then, now you can use the parallelogram law because the two vectors diverge from the point, so therefore this here is A minus B. Yes?
The parallelogram law or the parallelogram?
I formed the sorry, I mixed it up, didn't I? Okay, sorry about that. I'm not going to draw this again, okay? Let's just change. Thank you so much for your observation. Let's change this to parallelogram, and I will do triangle below, okay? Thank you. Okay? Let's do the triangle now. So let's draw the same two vectors. And I want to find A minus B. So again, you draw minus B in an opposite direction like that, so that you can use the triangle law. Remember, to use the triangle law, the arrows must follow each other. So if I put A like that, and then this is my minus B, I just reverse the arrow. Same length, but in a different direction. Now I can complete the triangle here. And this is A minus B. Any questions on the parallelogram and triangle law, knowing how to illustrate them? Okay, let's move on. Other properties. Scalar multiplication. Let C be a scalar. In vector calculus, when we speak about constants, we call them scalars. So C is really a constant, okay? So let C be a scalar. The vector CA, that is when you multiply the vector A by the constant, has length, absolute value of C, just in case C is negative, times the length of the vector A. So for example, if this is the vector A, then 2A is in the same direction but is double the length of the line. Two vectors, now this is a very important point because this is going to come up again and again. Two vectors are parallel if one is a scalar multiple of the other. So for example, the vector A is parallel to the vector 2A. Vector A is parallel to the vector negative 5A, as long as one is a scalar multiple of the other. And we will look at that in detail later. And here we have a blank page again, which we shall ignore. I have no idea how that happened. Let's look at components of a vector in a plane. I'm going to introduce you to position vectors. Okay? So, two-dimensional system, X and Y. This is the point A, and let's call it X1, Y1. Pardon me? Now this is the origin here. Draw a line from the origin to A. And put in your arrow. The vector OA, which is really the position of A with respect to the origin, is called a position vector. And it is usually denoted by the little a. So if there is a vector B, then the position vector would be little b. Okay? So this is the vector A. And so we say the vector A, which is the vector OA, you can use that as one way of writing a vector using angle brackets. The same point, but using angle brackets x1, y1, and that's in 2D. If it was in 3D, then it would be x1, y1, z1. Okay, so these are position vectors. So for example, if B is the point 3, 4, then the position vector B, which is OB, is 3, 4, angle brackets. So that's one type of vector. Let's look at displacement vectors now. If you are given 2 points, A and B, and these should be normal parentheses, not angled, then the displacement vector AB is given by the difference between the position vectors B and A. So B minus A, so you just subtract the respective coordinates. Let's do some examples. Suppose A is the point 1, 4, 2 and B is the point 3, 0, negative 5. Find the vector AB. So therefore the vector AB, the displacement vector is B minus A. So it's 3, 0, negative 5. Make sure you put angle brackets. Minus 1, 4, 2. And that is equal to 2 minus 4 minus 7. Another operation on a vector is the length of a vector. Finding the length or the magnitude of a vector. And here's the definition. The length of a vector A, which is the vector xyz, is given by, so this with the absolute value sign around it, don't say absolute value of the vector A. We see the length of A is the square root of x squared plus y squared plus z squared. Let's do some examples. Given V is the vector 3, negative 1, 2. W is the vector 4, 6, negative 8. Find A, the length of V. So the length of V is the square root of 3 squared, which is 9, plus negative 1 squared, 1, plus 4, which is square root 14. B, 6V minus a half W equals, just do exactly that. 6 times V, so you multiply each component by 6. 18 minus 6, 12, minus half W, 2, 3, minus 4, subtract, you get 16, minus 9, 16. Any questions? Okay, do these two on your own. The same two vectors, but find this. Can somebody give me your working for the length of the vector W, please? One person. Yes, give me the work, please. Very good. And that is square root of 116. Beautiful. Can somebody else give me the work for B, 2V minus W?
2V is 6 minus 2, 4, minus 4, 6, negative 8. That's 2, negative 8, 12.
Good. Questions? Okay, let's move on. Let's look at the standard basis vectors. And why do they call them standard basis vectors, by the way? Because any vector can be written in terms of these vectors. Whenever you see the term basis, and you will see that happening maybe in linear algebra, that means everything else, any point, vector, whatever, can be written in terms of those vectors or points. That's why they call them bases. So what are the standard basis vectors? The important properties that they have length 1. So what are they in R2? The notations are I and J. These are standard notations. So you don't use I, J, and K for any other vector in vector calculus other than these vectors. I is the vector 1, 0, and J is the vector 0, 1. So to illustrate, this is 1, this is 1. So this vector here is I, this vector here is J. So these are the standard basis vectors. And in R3, so in R2 there are 2, in R3 there are 3 of them, in R4 there are 4 of them, and so on, okay? In R3 they are given by I, J, and K. I is 1, 0, 0, so 1 in the X component, J, 1 in the Y component, Z, 1 in the K, 1 in the Z component, and zeros everywhere else. And as I said, any vector can be written in terms of the standard basis vectors. So for example, the vector 3, 4 in angle brackets can also be written as 3i plus 4j. The vector 3, 4, 5 can also be written as 3i plus 4j plus 5k. Let's look at some examples using these I, J, and K things. I want to find, well, given A and B, as you can see there, find A plus B. So let's do that. A, the vector A plus B is equal, just add the two. So that would be negative I plus J plus 2K. B, find the length of A minus B. So the first thing you need to find is A minus B, and then you find its length. Can somebody tell me what A minus B is? Go again. 3i, not negative 3i. Continue. Plus 3j. Minus 8k. Great. Okay, so we subtracting. Let's find the length. So the length of A minus B is equal to the square root of 9 plus 9 plus 64, and that is equal to square root of 82. Nice. Any questions? Okay, so try the other one on your own, and we'll go over it again. There are two different vectors. Don't use the A and B on top, okay? Okay. Can somebody give me your work for 2a plus 3b, please? Anybody? 8i plus 2j plus 3i minus 6j giving you. Where does the 5i come from? 11i minus 4j. Great. Can somebody else continue with B and give me the length of the vector A, please? Square root of 17, yes, but give me your work.
Square root of 16 plus 1.
16 plus 1, very good. Square root of 17. Any questions?
No.
Jacob, do you want to go home? Okay. Because every time I ask if there are any questions, you say no. Okay. Let's continue. Unit vectors. A unit vector is a vector whose length is 1. So all of these standard basis vectors have length 1. They are also called unit vectors. Now you need to be able to calculate the unit vector in the same direction as a vector. So if I give you one vector and I ask you what is the unit vector in the same direction, which unit vector is parallel to this vector? This is the formula. It's given by the vector itself, A divided by its length. The notation that we will use for unit vectors here would be A with the hat on top, or the caret. I think some of you in physics or engineering use U or another notation, I'm not sure. Yes. So let's do number 1. Find a unit vector in the same direction as A, which is I plus 2j minus 3k. So you first find the length of A, which is the square root of 1 plus 4 plus 9, which is square root 13. 14, thank you. At least you're awake. Great. And so a hat is equal to I plus 2j minus 3k all over square root 14, which you can write as 1 over square root 14i plus 2 over square root 14j minus 3 over square root 14k. Any questions on that? Then try B on your own, please. Can somebody give me the working, please? And so, what is B hat? And so you divide each of them by square root 29. Great job. Any questions here? No questions, right? No. Okay, let's move on. Let's resolve a vector into its components briefly. What do I mean by that? So let's draw a little picture here. X, Y again, origin. Draw a line from the origin to a point. Let's call this point x1, y1. And let's call this point A. So this is the vector little a. Okay? And then let's let this angle between the, let's put a little arrow here, sorry. And let's let this angle between the vector and the x-axis be theta. We want to resolve the vector, the position vector OA, into its components in terms of theta. In other words, we want to know what x1 is and what y1 is in terms of theta, right? Now, this is the vector A, right? So the length of the line would be the length of the vector A. Good? Now, if you remember your trigonometry, what is x1? Again, let me just draw a little right angle here for you. Good. So tell me, remind me, x1 is what cosine theta? Right, the length of the line, right? So it would be A, the length of A, cosine theta. And similarly, what is y1? The length of A times what? Sine theta. And so therefore we say that the vector A can be decomposed as length of A cosine theta times I plus length of A sine theta times J. This property is going to be very useful when we do something called directional derivatives. Okay, so you need to know how to do that. Any questions? This is it.